Marienbad, also known as classical NIM, is a two-player subtraction game made famous by the 1961 French movie Last Year at Marienbad. At first, it doesn't look that complicated. You get some tokens like cards or matchsticks and arrange them in 4 rows numbering 1, 3, 5 and 7. On their turn, each player can choose one row and take away any number of tokens, including all of them. The loser is whoever is left holding on to the last token. But Marienbad has a special place in computing history. 1 year after the movie, engineers in Poland programmed a computer, the Odra 1003, to play Marienbad against humans, and it won every single game. You might smell something fishy here. I don't know a whole lot about IT in the Soviet bloc, but computers in 1962 weren't exactly bright. The machine kept winning because Marienbad has a diabolical secret. It's an unfair game. If you're the second player, you're guaranteed to win as long as you follow a trick strategy. If you're the first player, forget it, Jack, it's Marienbad. You'll just have to cross your fingers that player 2 stuffs up with a bad move. Today, I'm going to show you how to program Excel into a Marienbad apex predator, guaranteed to mop the floor with any flesh and blood opponent stupid enough to make the first move. Because there's always a certain joy in building something artificial that can outwit and eliminate humans. You won't need any macros, just Office 365 formula language, but stick around and you might just fool laypersons into thinking that you've made Excel sentient. Each row on the table in a Marienbad game can be subdivided into chunks of 1, 2, and 4 tokens. When the game starts, there are 4 1s, 2 2s, and 2 4s. This means there's an even number of each kind of chunk. Every 1 has a partner, so does every 2, and every 4. The numbers 1, 2, and 4 are all powers of 2, but that's strictly trivia for nerds. Now here's the trick. When your opponent removes tokens from the table, look for the chunks that don't pair off with a partner, and add them up. This number is called the NIM sum, which is easy to remember because it rhymes with dim sum. On your turn, you should remove whichever tokens leave the NIM sum as low as possible, preferably 0. Keep doing this until the end game, when you get an opportunity to corner your opponent and leave them with 1 token. There are a few moves of 0 NIM sums that you should never make, but I'll cover those later. For humans, counting NIM sums takes a lot of mental arithmetic. But Excel is a computer language with a function called BitZor that does everything I just described. You feed it the token counts for each row, and it returns the NIM sum like magic. BitZor has a maximum of 2 inputs, but if you nest 2 daughter BitZors inside a mummy BitZor, it'll compute the NIM sum for all 4 rows. Because Marienbad has a maximum of only 16 possible moves, or 15 if you're player 2, it's an absolute piece of cake to brute force. Just make a list of all the valid moves remaining, check the NIM sum you'd get for each one, and choose the lowest. You'd need to work in a couple of other conditions to prevent bad moves, but that's mostly it. It's much easier than programming a computer to win at chess. But anyone facing down your program won't know if it's a smart algorithm or a dumb one. They'll just know that it keeps beating them, time and time again. All right, it's time to program Excel to be an unstoppable Marienbad monster. On this spreadsheet, I've laid out the initial state of the Marienbad game. And just on a pedantic note, I know these say rows. In Excel, these are technically columns because they're horizontal, but they're rows on the table of Marienbad, so that's what I'm calling them. And my objective today is going to build a custom function that can read these rows, the current state of the game, and return the best move. The neat thing about this function is you don't just have to use it in regular Marienbad games. It will work just as well if the computer plays first and you get a chance to beat it. And you could also use it in other NIM games that have different starting numbers. The only condition is that it has to be in 4 piles like this. So we're going to start by opening up a let function, which we're later going to turn into a lambda. And the only input we're going to call MB_rows is here. The first thing we need to do is cut them up. So cut them into individual piles. And I'm going to call one row 1, RW1, and use index MB_rows, skip the vertical input and horizontal input 1. And next, we're simply going to use copy-paste for these, because when we start generating all the different moves, a recursive function will probably be too much trouble. So just copy and modify row 1, row 2, index blank 2, row 3, index blank 3, row 4, index blank 4. Now that we've cut them up, we need to get a list of all of the possible subtractions you can get from here. And it's fine to start with the initial position. So let's call it subs1, and not sub1 because that's actually a cell reference, subs1. And for 1, there's only really one subtraction, so we can just use curly brackets to make it an array and make it 1, 0, 0, 0. That means subtract 1 from here. And subs2 is where it gets interesting, and we have to use hstack and 0 sequence RW2 0, 0. But we will have to fix a few things here. So let's take a look at what it looks like already. You can see all of these NAs, and we actually want zeros here, but otherwise we've got numbers of all the possible subtractions we could make. We could subtract 1, we could subtract 2, we could subtract 3. And we can get rid of these NAs with an ifNA or ifNA function. So the input is here, and if it's an NA, 0. So we now have the possibilities for pile 2 or row 2. But there could be another problem, because sometimes this number, in fact, it'll inevitably become 0 in most games. So that just returns an error. And we need to have a function to just return blanks for now if it's a 0. So we can use the if function, and a quick way to use it is a thing that's not commonly known about the if function is it doesn't need to take a condition as the logical test. You can just take a number, and if you put in a 0, it'll return value if false, as you can see on the screen. And if you put in any number but 0, it'll return value if true. It doesn't have to be a 1. Even if you put in 0.004, for instance, as the true, as the condition, and made it return this, if it's false, it'll still be returning calc, because that's an error. But let's make this a 1. There we go. And you can see that you can just use a number. So what this means is we can start generating if conditions for these. If RW1, so this will be either a 0 or a positive number. If RW1, the options for 1, and otherwise we'll create some blanks here to reuse. We have blanks. so blanks. If RW1, return 1, or otherwise blanks. And we'll do it for the others. If RW2, return this, otherwise blanks. And we can copy this and modify it for the rest. So let's copy this, paste, paste, subs 3, W3, W2 changes to 3, add 2 zeros behind it and a 0 in front, and that's it. RW4 will change to subs 4, sequence RW4, and there are no zeros in front of it and 3 zeros behind. And okay, we've got all of our subs, and we can now V-stack them. Subs 1, subs 2, subs 3, subs 4. The one issue, though, is that sometimes, let's turn one of these into a 0 now, they're still returning blanks, but it's still safer than returning errors, because otherwise errors would wreck the whole VStack function. So we're going to have to filter this, and we'll do that by renaming it V, and then we'll create an F for filter. But before we make a filter, we should note how the filter function works in Excel. Now, this might be recognizable to some people who use R, because there's an array and then there's a condition, and it's filtering rows where a certain condition is met. In R, this only works for data frames, if I'm not mistaken. In Excel, you can use any array, but the condition array has to be the same length as the array, and it also it has to be one dimension, so it has to be a row or a column. So we're going to be able to check blanks, we're going to do take V. Take has the same syntax as index, or the same inputs as index, so blank and take the first column. We can see that here, and then we want to check that this isn't blank. So we've got a bunch of trues and a false. So we can now use this as the second part of our filter function, and filter V, take that, and we have filtered it down into the correct number of possible subtraction. So we're going to rename this F. And next step is to get all of the possible return values, or the next state of the game if we play these moves. So we're going to call these options. And that would be MB rows. So these rows here, minus F, and return options. So you can see all the possible changes to the game. And we are going to get, let's have an example game here so we can start with the initial one. Let's take off 1 from the 4th row, and you can see if it's subtracting row 1, there's a 0, everything else is unchanged. With 2, there are options of subtracting 1 from row 2, 2 from row 2, 3 from row 2, others stay the same, and so forth. So this is looking correct. And now we just need to calculate the optimal move. So we'll do another value called nim_sum, and that's where we use the famous bitsor function. So we create a mummy bitsor and 2 kitty bitsors, all nested together. Bitsor, and first bitsor can be index, options, and 1. And we'll copy the index. So index options 2. And we make the second daughter bitsor, and index options 3, and index options 4. And this triple nested or double nested thing is going to return the nim-sum values. And this should show that we have a few that will restore the game back to 0 and a few that are higher. But we don't just want those, because we also want it to check if it can find a move that would end the game. So any move that would leave the number of objects in the game as 1. So we can have last card or last match or something. Last card, we want to take options and sum it by row. And what this will do is sum it, and so we don't have any that will subtract it all the way down to 1 and leave the opponent with the last card. But since I'll be putting this function on my GitHub and I want it to be accessible to other people, not all of you may have the latest version of Excel. There are a few versions of people whose spreadsheets are several versions behind. So I'm going to take the lambda approach, lambda A, sum A. Oops, sum A. So this works just as well, and that's returning the sums. And we also need some fail-safes, because I'll show you an example. Okay, so let's say the game starts off in its usual position, and I want to trick the computer through the nim-sum into a losing combination. So first thing I would do is take off 2 from here. Then the computer would presumably, this move would be, let's go and do a V-stack here just to show you. Actually, H-stack. Let's say you want options and nim-sum. So the natural thing that it would do to get a 0 to restore equilibrium after I've taken off 2 here is to take off 2 from the 7 and make that a 5. And then let's say I take off 4 from here and make this a 1 as well. Now, the natural response from going by nim-sum alone is to take off 4 from row 4, and that would leave 4 1s. But then that would be a losing game. I would take 1, the computer would take 1, I would take 1, and the computer would lose. So we don't want that. We want our AI or pseudo-AI or whatever to be a bit more brutal and not be duped into failing moves. And the way we do this is we want it to avoid any moves that would result in only 1s and 1s that are even numbered. So we don't want 2 1s left, we don't want 4 1s. So let's design a way to check that. So we're going to use by row again, and we're going to test if the row only contains 0s and 1s, so no numbers above 1. So by row options and lambda A and A equal to or under 1. So let's do that and see what we get. And in this case, yep. So let's actually do it so there is a 5 left here. And in some of these options, they're basically either taking off 4 or taking off 5 from row 4. So there are 2 cases where only 1s are left. And it's okay to have 3 1s because then you'll win, but it's bad to have 4 1s or 2 1s. So we want to do another test. Is even last card and multiply it. So this will return a 1 if there's an even number left on the table and they're all 0s or 1, an even number of 1s left on the table and nothing else. Okay, so we've got this, and that's warning us not to do that. And so what we're going to do, if you take off 5 here, even though it wouldn't be the best nim sum, you would still have a winning combination. The second player would have to, the first player rather, would have to take off this, then you could take off either of these and kill them. So we've got we're going to use this in an if function and call it failsafe. And if this, a whole test, then we want to add, we can just add the value of last card. We can add the value of last card to nim sum plus sum, otherwise nim sum. So what this now means is the best move is taking off all 5 and taking off only 4 because that's handing the gun to the opponent. That has been raised to a nim sum of 4 artificially, and that's the way to keep it to regulate the computer from not failing. And now we can start. We're on the home stretch, so we want to find the position of the winning move, and we'll call this pick. And we first wanted to search for any move in last card that would return a 1. So any move in last card that would leave only 1 piece on the table, because that's the killing blow. So last card, and I guess that's expressly what last card was there to check, and it hasn't found one. But on the other hand, if we did this and this, you would get the option of doing either of these would do it. So we've got that ready, and let's okay. And then we need to get an if now. So if it doesn't find the last card, we want it to search the failsafe and find the lowest number of artificial nim sums. So xmatch failsafe, actually xmatch min failsafe. We'll find the position, and that's it. We simply ask it to go to filter F, so that's our possible subtractions. F pick, and this will show the best subtractive move. Final step, build a lambda out of it. I have now built a proper gaming interface around the Lambda. You can get this workbook from my GitHub repository if you check out the video description. And I'm going to start trying to play my first game against Excel at Marienbad. Let's try remove 1. Excel removes 1 from the second row. I'm going to remove 2. Excel seems very close to having me cornered now. Let's remove 3. Okay. If you've played this game long enough, you know this is pretty much checkmate. Because if I get rid of these 2, Excel wins. And so far, I have not noticed any vulnerabilities in its playing ability, but if you do spot something that I haven't covered in my failsafe, some way to defeat it, then please leave a comment. You can also play against Excel as the opening player, and it'll automatically remove the first of these as the start player. Computers tend to do that. And in this tab, you do have a chance of defeating it. But I'm going to leave that to you guys. Enjoy the new year, and see you next time at Excelopithecus.